we can now go ahead and specify our measurement model. We know we have two correlated factors. We have readiness and in-exam self-regulation. We know that each of those latent variables have 4 indicators, which we will specify. We know that each item is loading onto just one latent variable, so that means there's no cross-loadings, and we call that a simple structure. And we can go ahead and specify that. Something I want to point out here, we are specifying a multi-group model, but this specification is identical to what we did in a single group context. So there's nothing fancy changing in our specification right now. It looks identical to how we fit our single group CFA, which is actually very nice. We don't have to change much. We don't have to change anything at all here. So I save this to model_CFA. I have the arrow, and then I have the quotations. And the quotation, right after the quotation, I have the hashtag latent factors. Don't worry about that. That's it's just a comment I made. Remember, R ignores anything after the hashtag symbol. And on that line, and on the next line, I have readiness and self-regulation. And then I have the 4 indicators, the 4 corresponding indicators for each latent variable. Notice again, case sensitive, I have the correct letters capitalized for each indicator here. And we also have plus signs separating the indicators. And then finally, we have the equals and the tilde sign for that is in front of each set of indicators. So once I have this loaded in, I'm going to fit the configural invariance model. And what's really nice is we're using the CFA function again. And model is the argument that we saw from a single group context. Data is the same argument we saw from the single group context again. Group is new. This is the only new piece, and group is going to be equal to school, again capitalized in quotations. And this is it. We're saving this to fit.config, and that's our configural model. And now we can go ahead and we can inspect it. So let's see what we find here. So right at the top, we have the number of observations per group, 500, 500. We have our fit indices. We can see here, CFI and TLI, they're both at 1. This is maxed out, but this is simulated data. We have RMSEA, which is at 0 exactly, and we have our SRMR, which is at 0.023. And we can scroll through here and we can see a couple of really neat things. So here's our data output, or our model output for group 1 or school A. And we can see here, once again, that R, as always, sets the first indicator of each latent variable to 1, which it has done. And we can see here, if we try to remember these loadings, 1.00, 0.913, 0.881, 0.661. And once we scroll all the way down to group 2, we can see that we have different loadings. And that makes perfect sense because the loadings and everything else is freely estimated. We could do that for the intercepts, which is really cool actually. We didn't have intercepts before when we were working in the single group CFA, but now we do. We have intercepts and we have our variances. And once again, these are our error variances proportions in this column std.all. And that makes those were ranged from 0 to 1, which we saw they are restricted in that way. We also have our intercepts and the standardized, completely standardized loadings for those. And we have all of that information presented for group 2 as well. So that's our configural model. And the fit of our configural model is great. And once again, the summary function that I ran is identical to the summary function that we would have run for a single group model. We have the fit.measures argument, we have the standardized equals true argument, and then this is just our model name, which here is fit.config. So everything looks good, the loadings look good, and if configural fit were poor here, we would have to go back to the drawing board. So we'd have to reconsider the model structure, rethink which items are mapping onto which factors. Is a 2-factor model even appropriate at all? Because it doesn't make sense to continue to test equality constraints on a model that's already poor. So now we'll move on to test the metric invariance, test for metric invariance. So all we're doing, and this is really neat, you're going to see how easy this is from a coding perspective. The theory, I think, is much more involved than actually coding up a model. So fit.metric this time instead of fit.config, and this is the same, model is the same, data is the same. group is the same as the configural model. All we're doing is adding this argument group.equal, and we're going to have it equal to C, which you'll see why in the next session. We're going to expand this out. Open bracket, close bracket, and between that we have loadings in quotations. And what we're saying is that we were now constraining our loadings to be equal across groups. So if you take a look now, that's it. We just fit the metric model, and now we're going to investigate whether those additional constraints have degraded our model and investigate the output of our model so we can see what it looks like. So if you take a look here, here's the start of that output, and we can have a look. We can see that our CFI and TLI are still at 1. Our RMSEA has jumped to 0.005. Our SRMR has jumped to 0.028. And now if we have a look at group 1 and we have a look at our loadings, 1, 0.925, 0.842, 0.739, and we scroll to group 2, 1, 0.925, 0.842, and 0.739. So now these are constrained to be equal to the corresponding loading in the other group, which is what we expected. And we can see that that's also true for self-regulation. So we have 1, 0.931, 0.876, 0.778. And if we scroll up here, 0.931, 0.876, and 0.788. So now the loadings here are equal, and we know that the fit of this metric model in and of itself is good, but what we can do is compare the fit. So we can use this ANOVA function. This is nothing to do with the ANOVA analyses from statistics. You can use this function for metric invariance in this context, and we can run it on fit.config and then comma fit.metric, because those are the two models we're constraining. And you can see, remember that this chi-square test is odd in that you want a non-significant p-value, and we have a non-significant p-value. What's really cool about this 6, as an aside, is this is the difference in our degrees of freedom, and this 6 comes from the fact that we've now constrained our loadings to be equal. And you may be saying, Natalie, but there's 8 loadings because we have 8 indicators. That's true, but remember that R sets each first indicator of each latent variable to 1. So because we have 2 latent variables and it's set 2 loadings equal to 1 already, the difference is between 8 and 2 is 6. So that's where that 6 comes from. So now what we can do is we can also identify the change in the fit indices. You can do this in a number of ways. You can just write out your RMSEA values from your configural model and your CFI values from your configural model and do the same thing with the metric model and subtract them from one another. I just did change it. I made you a function for changes in fit indices, and you can go ahead and run this set of code, and you can see here and the output using 122 that the change in CFI was 0 and the change in RMSE was 0.005. So those are beyond those guidelines that I mentioned earlier. So we are in really good shape. So we would say we can move forward in this analysis. Now we get back something now. We did all of this work of setting the constraints. Now we can get back the variances and the covariances. We are now able to compare those across groups. So we can do that. We can run the lav inspect function. Note that lav inspect, there's the capital I in inspect, and we can run that on our metric model, and we can type cov.lv in quotes as our second argument there. And we can go ahead and we can compare it. And we can actually reasonably look at the variances and covariances between groups and see which ones are larger. So for instance, we can see that readiness has a larger variance in school C than it does in school A.